Hello everyone, welcome to Researcher's Paradise. I am Sorish Das, and in this video we will be learning about SEH exploitation. So the agenda of this video is, first we'll understand what is SEH. We'll also look into the working mechanism of a typical exception handler. Then we'll understand the structure of SEH chain, which will enable us to determine how to exploit the SEH. Lastly, we'll see the tools required for this demonstration, and then we'll culminate by watching the demonstration of this exploit. So to begin with, what is SEH? SEH is structured exception handling, and it is a Windows OS mechanism. So in this, the system makes use of a linked list style data structure to maintain a chain of exception handlers. This linked list is also called as an SEH chain, since the next exception handler is chained with its predecessor exception handler. So basically in the linked list, the data record is nothing but the exception handler, and it also contains a pointer to the next exception handler or the next SEH. Now when the OS faces an exception, it has two options: either to resolve the exception right away or run down the list of exception handlers and evaluate other exception handler functions which are suitable to solve that particular exception. To perform this action, the exception handler requires two things. Number one, a pointer to the current exception registration record, the SEH, and a pointer to the next exception registration record, or the NSEH. Since our Windows stack grows downwards, so you may find that the order of these records is reversed. So NSEH will come first, and then it will move down to SEH. When an exception occurs in a program function, the exception handler will push the elements of its structure to the stack, since this is part of the function prologue to execute the exception. Now, in such a case, if we want a program to store an overly long buffer and try to override the structured exception handler, Windows will zero out the CPU registers, so we won't be able to directly jump to our shellcode. So as you can see here, that the SEH and NSEH both contain total of 8 bytes. Hence, at the time of exception, the SEH is located at ESP plus 8 bytes. Now you may think of that like in earlier exploits, the earlier video that we saw, that if we simply just overwrite the buffer, it will cause us to launch our shellcode. But in case of SEH, it won't happen. The Windows will just completely zero out the registers, and it will not solve the purpose of SEH exploitation. However, the protection mechanism of SEH is flawed, and we will make use of this flaw to construct the exploit. So what we will do is we will override the SEH with a pointer to a pop ret instruction. The pop instruction will remove 4 bytes from the top of the stack, and the ret instruction will return execution to the top of the stack. So 2 pops means we are popping the pointer to the exception handler, as well as popping out the value of pointer to the NSEH, which brings us to the top of the stack, or the starting, the ESP. Now, so as SEH is located at ESP plus 8, so if we decrement the stack with 8 bytes and return the new pointer to the top of the stack, we will then be executing the next SEH. And then we also have some 4 bytes in space available at NSEH to write the opcode that will jump to an area of memory that we want to control. And since we are making the program control jump to a controlled memory area, it is at this location we will insert our shellcode, and we will cause the shellcode to get executed and the program to get crashed. I know this sounds a little complicated, but it will be much clearer when I show you the demonstration. Before moving on to the demonstration, let's revisit the tools that we need. So Windows 7 32-bit VM would be our victim machine. Kali Linux VM would be our attacker machine. VS Code will be used for code editing purposes as well as for analyzing certain output files. And I request you to install the VS Code in both the attacker as well as VM machine for better execution of the exploit. Then we need to install two more softwares in the Windows 7 VM. One is Immunity Debugger, which will be used for debugging purposes, and DVD-X Player 5.5 Pro, which is our vulnerable application. Let us now move to the demonstration of this exploit. So here I am inside my Kali Linux VM. I have created a simple Python file which will just put 2000 A's inside a PLF file. A PLF file is nothing but a playlist file, and save it and compile it. So as it's a simple Python file, you can just compile by just typing python exploit1.py. Since I've already done it, so I leave that to you. And then I move to my Windows 7 machine VM. Here I open the command prompt, and using the wget utility I will fetch that file. So I write wget http So this is the IP of my Kali Linux machine, and the exploit is stored inside the SEH exploits. So basically what it is doing is I'm running an Apache server on my Kali machine, and in that Apache machine, over there I have hosted a folder known as SEH exploits, and within that SEH exploits I have the exploit files. So I import the first exploit file. We have it down here. I'll move it on the top so that you can see clearly. Now I will go to Immunity Debugger and then open the DVD player exe file, this software. I press F9. And then I will open that playlist file which I have just imported. So as you can see that the ESP gets overwritten with multiple A's as well as the EIP. But in earlier cases we used to simply leave it there and we didn't let it pass the exception. But in our case, since the crash has occurred, but we need to pass the initial exception by pressing Shift F9. We do this because this initial exception leads to a different exploitation technique, and we are interested in SEH. And if I show you the SEH log and handler log, you can see that it did try to read 41 the A's, but when the address became 41s, it has shown a corrupted entry. That means we have successfully tried to exploit the feature of SEH, but some more steps are remaining. I minimize it. Now I again restart the application, and now what I will do is, now since simple A's won't help me determine that exactly where is the offset of the application, so to make it more concrete, I will use the Ruby script pattern create to create a pattern of 2000. Here is it, the usage pattern create.rb. You can just find the path to this pattern create file by just typing anywhere in the Kali terminal. So it will give you the exact path where it is there, and as you can see I am in the exact path where this Ruby script is there. and this is my cyclic pattern. I include this in the second file. I write it into a second exploit2.plf file and simply just compile it and ship it to the Windows 7. Again, I'll go to the shell and here we have our second file. Now I'm at the entry point. So now I'll start the application inside Immunity Debugger. Open the playlist file. So now this is complete gibberish. Right now we can see that ESP is being overwritten with that J3AJ and EIP is being overwritten with 3769. Option would be to find the offset would be to use the Mona script. Then the command is Mona find MSP. Before I run that, since I've already practiced this exploit once, so I'll just remove the previous files that are present. Otherwise it may cause a little conflict in the file formatting. I hit enter. So it will take a lot of time to find the different pointers, but we are currently doing what? SEH exploitation, SEH chain. So our only point of interest is this SEH record, the NSEH field, which is overwritten with a normal pattern, and this is the offset 608. That means up to 608 I can fill up the A's. Then it will be followed by 4 bytes which will occupy the NSEH, and then I'll include my SEH value. Now in the SEH part, if you remember from the slides that I showed you, in the SEH part we have to overwrite it with a pop ret instruction. So we can again utilize the Mona script to find that particular instruction by just typing Mona SEH. It takes a little bit time. And now this is my directory where the SEH file has been generated. I will use VS Code to analyze that file. So it gives the different module info, and then once the module info gets finished, then it will give us the instructions, pop reds, as you can see. Now I recommend that you don't take an instruction like this which has some extra return, because it will cause like reverse removal of certain bytes from the stack. And if you see from line number 147 till 166, one or every value in my case has a 0 in it, and a 0 in your opcode can be sometimes troublesome, as it may be interpreted by the system as a null character, and it will cause breaking of your exploit. So what I'll do is, this seems to be a safe value, and I will take this, and also it is also just returning ret. And if we scroll down more to the right, the safe SEH is also false, and the file belongs to a DLL which is of this particular software only, epg.dll, which is part of the DVDX player software. Thus it will make my exploit universal. So I'll just take this file, and it has to be included in my exploit in little endian. So first it will be 19, then 76, then 61, then 61. I go back to my Kali machine. I include this address 61, 61, 76, 19. I'll show it once again to verify. So it is 61, 61, 76, 19. And for the time being, let me check whether this value is properly causing the overwrite of SEH, and I'll set a breakpoint at this particular address, and then I'll on the during the execution of this exploit via immunity, I will find what value I need to the opcode that I need to overwrite on the NSEH part. So you can compile the file. It's a simple Python file. It will give you a .plf extension file, and once you have that, I'll restart the application. And mind you, since that opcode, that pop-up return instruction was taken from an application DLL, so unless and until you don't launch the application by pressing F9 inside immunity, you won't be able to set the breakpoint. So breakpoint can be set using this. What was the address? 61617619. So as I hit enter, it will give a chime sound, which means the breakpoint has been set. Now when I will open that playlist file, the third file, it will go and stop at that particular address just before our the D's where it starts. Okay, I need to now import that file. Exploit 3 is now there. Now I open the file. And now if I do so if as you see that the pop-up return has been hit on the top left corner. Now I step using F7, and if you now I am at the 4 B's just before the SEH. So this is where I need to now include my NSEH. Now NSEH should contain a opcode which will enable me to jump to the part where the D's are starting, or where I'm trying to manipulate the ESP. That program is trying to manipulate the ESP. So what I'll do is but I don't know the opcode, right? So how to determine that? Just go to this particular address and just press spacebar, type jump, and this particular value 0012F578. 0012F578. Assemble. So it shows that we are making a short jump to the 78 value, and the opcode is EB06. So you must be wondering that how do we now fill for the 4 bytes that are there. So we can simply include knobs. 2 knobs would be sufficient, right? X90, X90. So that is what we will do. EB06, X90, X90. If you see here, I have included that EB06, X90, X90, followed by that particular pop-up return value, and then in the buff I have written my shellcode preceded by the knobs. Now you can generate the shellcode by using the MSF Venom command. Here is the command: MSF Venom -p windows/exec. Command is calc.exe. The file format should be Python. -a architecture is 32-bit and should exclude these bad characters. So this is the shellcode that is generated, and I have already included that here. So I need not include it again. You can include it, and then simply just type python exploit4.plf, and it will python exploit4.py, and it will generate the playlist file. Now I come back to Windows and restart the application here. Before restarting, I would import the 4th playlist file. It is here. Now I'll press F9. So it has started. Now I click on open playlist and select the fourth exploit file, hit shift F9, and that's it. We get our calculator, which is the shellcode that we wanted. And if you now see that the exception has been handled because it did not follow the current path and it did not give the report of corrupted data also. And the application has terminated and the shellcode got executed, so calculator popped up. We can also change this shellcode to contain a reverse shell on VM for the Windows machine. So to do that, you just have to simply change the shellcode. You can change the shellcode with this particular msvenom command. I'm using Windows shell reverse TCP and I've set the Kali's IP as the listening host, and 4444 is the port that I've allowed on my Unix firewall. So I hit enter. It takes a little bit more time as compared to the Calci because it's a reverse shell. So as you can see, it's of 351 bytes payload, whereas it is of Calci is just of 220 bytes. So it does not contain the bad characters also, and I've included it already. The remaining structure remains the same. Just compile it, and before you compile, keep your netcat handler ready so that whenever the exploit runs, you should be able to listen to it. I have kept it ready. Now I come back here, I download my fifth exploit file, and since it is terminated, so I need to restart this application. Now the reverse shell, it will occur the moment I pass the exception, when I press the shift F9. So currently and I need to import. I have already imported it. It's here. I load the fifth file, and now it is about to hit the exception. So before it does that, I'll start the netcat listener, and then moment I press shift F9, I get my Windows 7 shell. So as you can see, with the help of system info, I'm able to verify that I've got this particular VM access, the Windows 7 OS access directly. So that's it for this demonstration. Thank you for watching this video. Please do share your feedback and comments. Thank you.